Okay, so there should be some exercises that yesterday I didn't have time to suggest you. So for example, this one. And then we conclude. So suppose fn greater or equal than 0 and the integral of fn converges to 0. So this is equivalent in this setting to fn converges to 0 almost everywhere, fn tight, and uniformly integrated. Actually, solo con tautologica. And then this is more interesting. So for example, fn in measure on a set E whose measure is higher. Prove that it is equivalent to the integral of fn minus f 1 plus fn minus f as to 0. Okay. There are other exercises, but I think they are not that smart. Okay. So, in order to recap all the stuff, so what we did, we have so the Lebesgue the Lebesgue measure on R. So we find also the sigma algebra of measurable sets and the measure M. Okay, then from this guy we have the regularity. Well, we say when a function is measurable. We have the regularity, which is losing Takeoff. Then we have the notion of integral. For positive or L1 functions. Then we have the convergence, which is essentially we have Fatou lemma. Then we have the Lebesgue dominated convergence. And well, the monotone convergence. Monotone for positive function, which is very positive. And as a variation, we have seen that you have different notions of slightly different notion of convergence. So, for example, we have the convergence in measure. And then also we have the other notion of, well, when a family of functions is uniformly controlled. Here is uniformly controlled by here the assumption was that Fn is less than a function g in L1. And in order to relax a little bit the thing, you have the notion of uniform integrability. Which is a very important notion, because essentially it tells you the mass cannot escape to plus infinity vertically. And if you want to control the mass that escapes to plus infinity horizontally, you have the islands. Okay. So the language, essentially all these theorems, they hold whenever you replace the space with something which is just a space with a measure which is sigma finite and what some regular. For example, RB with any other measure here, and here you put the Lebesgue, the Borel sigma algebra. Remember that this thing contains the Borel. Okay? And they are not too much different. Okay, so now we go on, well, now we have the two possibilities I told you yesterday. So either we go on with the measure theory, so we take general measures which are more complicated than this one, but this is the cornerstone of the theory, no? Because it's exactly what you need. Then, okay, you do the product, and then you discover you can have a more complicated function like delta, a measure like delta Dirac, or even Cantorian, or Hausdorff. But still, all the theory works in the same way. And we have to cover a little bit, because at least to see that all what we did now, the proofs, they're not changing. And the proof indeed, apart from some use of the intervals, they are always the same. If you rewrite the assumption depending on your open sets, it works. They work. But on the other hand, now that we have a notion of integral which is more general, we may ask the question, so how about the integral of f fundamental theorem of calculus. You see, it's natural because now we know that we can take f in L1, so the space whose the integral of the modulus is finite, and we can give a meaning of this object. So we can give a meaning of this object. And the question is, which class is this one? So it's C1, well, C1 certainly an inside, but they do not need to be C1. It's, I don't know, just continuous, or it's an intermediate class. Okay, so before going with the theory, one has to do some example and see what you can expect here. Okay, so first of all, let's take f. Well, now we know f in L1. So and now we can write f as a sum of two parts, no? The positive and the negative part. And by definition, being L1 means that the integral of both is finite. So this implies f and is the very definition. So let's put the thing here. The integral is linear. Okay, but what we can say about this function? What can we say about this function?
It's increasing.
It's increasing. Yeah. Simple. So we discovered that if this formula holds, f is the difference of two increasing functions. Okay.
Yes, that's plasma. That's a positive part.
Yep. The negative is the same. So we discovered the following remark, which is very important. If f is the primitive, then f is the difference of two increasing functions. Okay. But so let's see. Just to take the following example. Let's say I want to ask if the following function, so is one, so is the primitive of an L1 function. So the function is continuous. I want really to understand if I can do everything for continuous, or really the theory is more subtle.
This, I think, can be written as a sum of. Oh, no.
Okay, well, you are fine to differentiate, but in zero. No?
Sorry?
Well, I can use the classical theorem, but in the point zero. Classical derivative. So f prime, which is equal to f for x different than zero, I just compute. So it's sine 1 over x minus 1 over x cosine 1 over x. And then, so essentially this is an L1 function because, this is a function which is measurable. I define the function out of a set of measure 0. So it is defined. I just said in 0 put whatever you want. The integral is not going to change if the integral exists. I compute a little bit. So, but do you think is f in L1?
I think yes, because the trouble, the problems, the points where there are problems are measure 0 or something like that.
But you are looking to integrate.
Okay.
Yeah, you are saying it is measurable. Yeah,
I think it's also bounded.
Yeah. Wait a minute. Then stop bounded.
Yes.
Is that integrable?
No.
It's not integrable. Because essentially, just take the positive part, and well, you have this slope. If you compute the sides, moreover, and hey, you take the triangle, then you discover that this object is of the order of, is of the order of the integral 1 over x, 0 to 1. So the theory is non-trivial. It's not any continuous function. There is some class in between that makes the tuple. So let's go on with this direction. So now we ask another exercise. Define here we can put minus infinity, doesn't matter. Okay. What they need to prove. This is the continuity, no? At least on the right, and then you have the continuity on the left, which is the same.
We need some condition on that.
That is signal 1. So we have already proved that if I converges to 0, the integral over to the empty set, the integral over I of modulus of f converges to 0. That's it. Okay, so we discover it is in simple computation the following. So the primitive f of an L1 function is a class which contains C1 and is contained in C0. So we need to find what is this class over there. It is a very important class, because it's the class for which the fundamental theorem of calculus holds. And so it's not a trivial case. Okay, so let's. But then we discovered already that monotone functions they have the basic construction. So the basic analysis is done for monotone functions, because if f is the primitive, f is the difference of two monotone functions. So I need to study monotone functions. Okay, so now we analyze monotone functions. It's okay for you. So this is why I need to develop this theory. Not that I will work out one more. It's really a fundamental question. Okay, now, for us, the monotone function will be always bounded in a closed interval. You can take open intervals and unbounded, but then it means that it's bounded in any compact subset. Okay, so let me say the following. So the exercise f from A, B goes to R monotone. Then f restricted to C, D, and C greater than A. Okay, less than D, less than B. R is R. But it seems like a joke. Okay. These are values inside the interval, so f assumes some value here and another value, and then the value in between by monotonicity they should lie, well, either go up or go down, doesn't matter. So essentially the theory is interested in compact sets where f is bounded at one. So let's give now the definition. Sorry, the definition is that one. Sorry. So let's give the following. So let's say f. Let's find a b into r. Okay, it's not the definition. It's that really we consider bounded and increasing. For decreasing one, you just take the minus sign, no? So, first proposition. So, first question, are monotone functions continuous? If you remember the inclusion there, we know that the integral is continuous. And then another question I may ask. So I know that it is the difference of two monotone functions. So give me a monotone function. Is the class of monotone functions contained in continuous, in the continuous functions? Question. Example?
Yes.
The Heaviside function is the easiest. However, we have the following f monotone as above. So for us, this means monotone. Then f is continuous outside. Okay, you give me 1 point. How many points?
Not too many.
Not too many. How many?
Finite. Finite.
Finite?
Fine.
Okay, let's see. You understand this drawing? I go up by 1/2, 1/4, 1/8, 1/16, and go.
Oh,
How many?
contrary.
Count. Question. So my question is, can you give the proof? Just invent it.
Yeah. It's based on this.
Mm-hmm.
If the jumps are uncountable, then this would jump to infinity.
Yeah. Yes. I can accept it, but
You want to put it in words?
because if the number of jump is uncountable, then how to? It's yeah, the idea is correct. However, I think we don't have symbols. No, now what I mean, the sum of an uncountable thing is not defined. So what do you mean? But it's true, it's true.
Okay.
So maybe we can just count the jumps which are larger than a fixed size. It's easy. This is a positive. But the philosophy is the same, no? If it is uncountable, one of them should be larger than, should be uncountable. But okay. So let's say b minus f of a, let's say this is equal to t. There is a symbol here, but we need to translate. Let's say this is equal to n, greater or equal than 0. So the number of jumps larger than, let's say, epsilon. So how many upward jumps I may have which are larger than epsilon?
Only if I make the jump should be less. Should be less than m. The total sum of jumps should be less than m.
The sum of jumps, which is the number times the size. So I start from this value, let's say in A, and in B I write this value, and I just look jumps larger than epsilon. So each of these intervals here has size epsilon, no? And this is f of A, and this is f of B. How many of them? They are disjoint.
They're at most f of b minus f of a over epsilon.
Okay. So this is observation 0. Hence, how to finish the proof?
Epsilon 1 over n, and we take the counter proof.
Of the set is countable. Countable union or countable sets is countable. Okay.
But I think we should show first that the function, an increasing function, can only have jump discontinuities, not other type of discontinuity.
The limit exists. Yeah. The right and the left limit, they exist. Yeah, this is the fundamental of the proof. If we have to ask to add the following. In the rest, the limit exists. So, in fact, there is this following lemma, let's say. If f is increasing or decreasing, is monotone. For all x, the limit for y goes to x of f of y exists. And the limit for y which goes to x of f of y exists. So let's say this is f at x plus, f at x minus, and f of x is between f of x plus and f of x minus. Yeah, you're right. This is so how to prove this lemma? Because this object is decreasing, so the limit exists. And now, what are the jumps here? The jump, it means where f of x plus minus f of x minus is larger than epsilon. So in the rest, f plus is equal to f minus, fx plus is equal to fx minus, so they don't sum.
It's monotone and bounded, so we can use the sequential monotone convergence theorem.
Which one? This one?
Yeah, any sequence.
Yes. But this is once you fix the y, so the value is below the limit for y. So it's really the definition here. This is really the definition.
Yes.
In my opinion, the existence of these guys. They decrease. And then if you take what is the limit for any sequence is the limit of the whole.
So
I don't see what is the trouble in the existence of this limit here. Do you have any trouble showing the existence of the limits here?
We already know that this is bounded.
It's bound.
So the limit increasing,
Yeah.
so it must exist.
Okay, if you want to fill the details that they are not here, it's
Okay.
limited, it's increasing, and if you just shrink everything, is like this, so the surface is decreasing or increasing. Okay, now we do something which is a little bit more delicate, and this is really something very deep. So is the Vitali is the covering theorem. So let F be a collection of closed and bounded intervals. Then we say that F covers E, well, not necessarily E, a subset of R in the sense of Vitali, if for all epsilon, for all x, there exists an interval E in the family with the property that x belongs to the interval and the length of the interval, or let's say the measure of the interval, is less than epsilon. So essentially, it is telling me that I give you a family of intervals, which during the proofs will always be the good intervals. For example, if you take a limit or a lim sup, you know that has a sequence which converges, a subsequence which converges, and that subsequence will play the role of the good, will give the boundaries of the good interval, the extremal of the good intervals. And you're required to be, in some sense, there is a word here. Okay, we cannot. You require that they can be taken as small as you want. Okay, so let's see the lemma. And we understand how you use this property. Yeah, it's a fine covering, something. They call this property is a fine covering. Sometimes that's the if the external measure of E is less than plus infinity, and F covers E in the sense of Vitali, then there exists a finite collection in F, then for, let's say, for all epsilon, there exists a finite collection such that the external measure of what is left outside is less than epsilon. Okay, so now we do the proof by drawing. And then we try to, at the end, fix it, because one has to understand how to start. As usually, if you face this problem, then you have to understand what is the key point. And then you can do the proof. It's not like I can give you the proof, but then it's not your job in the future, no? Because one has to find proofs. So you face this theorem, and so let's start. So let's see if this is E. And now I have to choose the sequence. And essentially, I would choose the sequence because at the end the corollary will be that I have a sequence now countable such that the difference as outer measure 0. So as measure 0. So this is just a step to the general theorem, but actually let's see how to do that. So I need to cover this, and then I have to, there are disjoint. This is important. Okay, so let's start. How to do that? An idea? Right? Well, I have to take one. Let's take one. So let me put one interval here. I have no rule up to now, any idea how to choose one. So, and then I deduce which is the rule that helped me to do the thing, and then maybe I understand how to do the proof. So already in the choosing one, which one you would choose? The largest, the smallest. So it's not like you, let's say you have to paint a wall, and then, or you have to attach stickers to the wall in order to cover all the wall. And which sticker you choose first?
We don't need to choose an epsilon or something like a size to cover.
On which one?
Yes, but I mean in the beginning of this sketch. No?
The epsilon here.
Yes.
Well, yes, but you don't know which one you have to remove. Yes, fix epsilon, but in any case, the thing is that you see from if this hold, you take the countable sequence in the limit and this get 0.
Is it a countable or finite sequence?
Finite in the lemma. And then you can deduce that for countable I can require this to be 0. And then they are equivalent, no? Because if countable goes 0, finite goes essentially to the whole measure and vice versa. Okay, so let's think about it. I have to cover this with stickers. And I have stickers of different sizes, which is here. They can be not too large, but they can be as small as I want. Which one you attach first? Any idea? Which one would you attach first?
Okay.
The biggest. Okay, so I take the one the biggest, but maybe I don't have, but okay, this is, so let's area I be the biggest, I1 be the biggest. Okay, so I don't need to cover all the rest. So everything which is inside, I need now to cover, which you choose the second one.
The next biggest.
Yes, but maybe the next biggest intersect E1.
So try to cover what is outside.
Be the,
This switch can cover points outside.
yeah, be the biggest on the intervals, in the intervals, in F minus the I in F such that I intersect I1. So if I cover, so let's say this is I2. Okay, if I cover it, it's fine, otherwise I have to go on with the next. Okay, so in this way, I construct a sequence of disjoint intervals with the property with the length of I I n is less or equal than the length of I n minus 1. I always choose the biggest.
It's not the opposite inequality.
It's not?
No, it's okay.
It's okay?
Yes, because first you take the biggest and then the next one is smaller.
Yes.
Okay. Now, this is the first observation. This is my choice. So now what I can say, and now it comes to the measure theory here. So E has an outer measure which is finite. So what I can say about the sum of the length?
It's less than the outer measure. It's less than
Less than?
outer.
Essentially it's a constant, it's finite. It's finite because at the end I have only to cover the wall, I don't want to cover the whole institute. So less than plus infinity. So now I see already something, no? That essentially the tail of this one will be less than epsilon. However, I don't know if the tail covers the rest of E. But then let's make use of this guy. So let's, I need some space. Let's remove this one. In any case, we have to make the proof a little bit more fun. Let's go on. So let X be in E minus the union of all sets. Or let's say, let union up to N. So I'm asking and take I of X is one of the intervals in the Vitali covering. The Vitali covering. Which means that X is in I of X. And well, I can choose, well, that's one of the sets. And I of X is not in the sequence. So why I'm not choosing I of X?
Because it has length lower than the others.
But the length goes to 0. So why is not being chosen up to L? Either the length is small or 0. If the length cannot be 0, if they are not degenerate. So let's put here plus infinity, just so we understand why at the points which are outside. At some point, so here are the two conditions. Is either its length is smaller than the biggest, or it is intersecting. Okay? So if it is not chosen, it means that I of X intersect one I of I with, it can intersect one which is smaller, because then I would have chosen at the earlier step. So I have for sure that L of I of X is less than L of I. This is just if you think, I start with the largest one, then I look. There may be something which has the same the same area, the same dimension of the sticker. But I'm not choosing it because if I attach it, it superimposes my previous one. Then I discard. And when I discard this set, well, it means that maybe one part of the wall is not being covered. But certainly is not being covered simply because the choice of the sticker is such that it covers my previous sticker, so the length should be less than this guy. Because otherwise I would have chosen, instead of the intersecting one, this guy. You understand? So let me repeat. I start with the largest. And then I discard all the sets I choose with this one. I discard all the intervals whose length is like this one. And intersect this one. This is okay. Then I choose the next one. The next one cannot have a length which is larger than this, because otherwise it wouldn't be chosen. So if it has a length which is larger, it should intersect the first. But then my choice is the biggest. So among what is left, I choose the biggest, and so what I'm throwing out is something which is smaller than this one. Then I can choose another one, which is lower, which is the biggest among the ones that do not intersect. And then I'm throwing out all these intervals whose length is less or equal than this guy, otherwise I would have chosen. Or if it is larger than this guy, then it should intersect this guy, otherwise I would have chosen. Or if it is larger than this guy, I intersect this guy, otherwise I would have chosen. Okay, so we have this property. I'm sorry, I'm trying really to make you to feel the proof. Because this is it's easy to okay. So now, once we have the proof here, the situation, what I can say about this thing. So let's say this is I of x. And then, okay, let's say that this is centered at this point, and then I have, sorry, this is I, the one that intersects, and this is I of x. So do you observe something? Let me tell you, because it's always I have to think. If I enlarge I by some factor, I cover it. It's okay, no? From this condition, it means that, let's say, I3, which is enlarged by a factor 3, contains the IX. So the proof is due to Vital, it's not a stupid guy, so it cannot be that easy. There are several pieces, no? Do you agree? Yeah, because the length of this guy is less than this one. So, and intersect. So if I enlarge 3 times, certainly I have the thing. So what I discover that, okay, once I have chosen this sequence, the union over n of the intervals in enlarged by 3 times, they cover. Do you agree with this? So essentially, I built a sequence. They are disjoint, the derivative is decreasing, the sum is finite. If I enlarge them 3 times, they cover all my set. How to conclude now? I give you the hint.
How do we choose the first one?
Biggest.
biggest.
Okay, I give the hint how to conclude. So repeat just a sentence. Let's see what you understand. Repeat for E minus the union of up to capital N of II. So that the sum from n plus 1 to plus infinity of the length of I n is less than epsilon divided by, okay, I love 3 times divided by 3. Why? Because if I remove the first n intervals, then I can restart the procedure. The procedure is restarting, exactly the same. So I do the same choices. But then I discover from this observation, that the intervals that I choose from that time onward, they cover what is left. But what is left, and then the measure is contained by monotonicity, the measure of the union, which is also equal to the sum of what is left. And what is left is, well, since the sum of the length goes to 0, I can choose n such as what is left as measure arbitrarily small. So from this plus 3 times, you get that the outer measure of E is less than epsilon divided by 3 times 2. So, okay, no, it's not okay. Okay, there are some, now let's fix what is not working at this point. So this is the line, now we have the line. Now what's it? So the maximum of the length may not exist. The supreme exists. So how to do that, to solve this problem?
It's closed.
They are closed, but not the values of the length. No?
Sorry?
The intervals are closed, but the length can be just a family, numbers. Okay.
Yeah,
But you said that the supreme exists.
Hmm?
The supreme exists
The
because
supreme exists, so
the E has outer measure finite. No.
I need to take that the E are larger than 1/2 the supreme. So here I replace, so let me, so that E, the length of E larger than 1/2 the sup of the length of the family. So here I replace always 1/2, no problem. This is okay. This is not okay. I certainly, the next one has length which is less or equal than 1/2 the previous. Cannot be twice, otherwise the supreme is larger. But we actually did not use that too much. The sum is finite. This is something that, well, you have to be sure that your choice is okay. How to do that? I need to use that the outer measure of E is finite.
Yes. I mean, one is that. The other is because they are 1, 2 over the power of 2.
They could be
The
always the
length
same.
of the
If they
first.
are constant, the length is constant.
By definition, we take them disjoint in a bounded interval.
Hmm?
They're disjoint in a bounded interval.
Yeah, that's the point. Indeed, you can take E is contained in O with the measure of O less than plus infinity, and O is open. Okay. So now what you can take, you can require that each EX is contained in O. Because it is a fine, remember this is a fine covering, so each X has a neighborhood which is no. And being a fine covering, I can take the interval as small as I want. So what I'm saying here is that, well, you don't want to put something which is very large around because you have so much space. If you fix the boundary of the set, you can always find stickers which stay inside your boundary because it is a fine curve. So you can choose stickers that go in each point as small as you want. And from this one now, it's this measure is less or equal than the measure of O. The bounded integral is the idea, but actually it does not. It depends on you that you can choose something. So let's go here. If I intersect one of the previous choice, what I have here cannot be larger than 2. It's written here. Because if it is larger than 2 now, I should have chosen. Now, instead of having 1, when it is the biggest, is 2. And so let's look here now. This set can be twice. What is the scale? 5. If this is 0, 1, then I can add the length which is 4, so I go up to 5. So the scale now becomes 5, 5, and here 5. I spent one. But it's really, the proof is complete, it's not immediate. And indeed, you have always to think at the beginning, what is the idea? So, well, I cannot say you digest the proof, but you feel the idea, no? The starting point is always to choose the largest one which does not intersect the other. And the rest is technique. So that choice and this observation. The rest is just technique. Okay? Okay, so let's do some exercise immediately, just to see, to stay warm of this proof. The outer measure of E is equal to 0, then, less than plus infinity, then there exists an F is a Vitali covering of E, then there exists I countable contained in F, disjoint, and the outer measure E minus the union is equal to 0. it's already dilemma, no? It's already dilemma. Because this object is less than the I from n for any n, and I can choose n large so that this is less than epsilon. Okay? And then exercise, if I alpha is in R now, is uncountable family of closed, bounded intervals, then the union of all these intervals is measurable. This is something strange, but I can tell you that instead is the fact that set of measure 0, you can add them, and they don't matter. Indeed, the extension is that if you take any countable family of any uncountable family of measurable sets, then up to set of measure 0 you can find that the union is measurable. It's strange, but actually it's the case. Okay, but let's stay here. So how to prove that? So let's say the observation I alpha, so the family I alpha is a fine covariant of the union I alpha. Well, it's not affine, but let's say is a, well, we can add, in fact, this is a version should be fixed, but we can't. I'm adding to each E alpha also the subset of the so-called set of converging to 0. And then it becomes a fine covariant, no? I need to add something, but essentially the idea is that, yes, it's a fine covariant of itself. And then, let's apply the statement. Then there exists a countable family, countable and disjoint. Well, the theorem tells me disjoint. If I just want to use the I alpha, I don't need to take them disjoint. Such that the outer measure of the union minus the union of the selected one is measure 0. Then is measured. Huh? Strange, no? You know, sigma algebras are not closed for uncountable unions, but actually, yeah, basically yes. One has only to express the stuff. Okay, once we have this in hand, we can come back to monotone functions. Why I need a theorem like this one? So now I'm writing a definition, and let's see if you understand why a theorem like this one is needed. If f is from A, B to R, let's say open now, because I want to have the both limits, otherwise define the upper derivative in the point x is the lim sup. Okay, and here I say h go to 0 of h positive of the sup sorry, this is the limit then, because the soup is here from, what do you call it, T. And lower limit, lower derivative. Do you see in this definition some family like a Vitali family? But we don't see clearly because it's a jump. But this gives me a sequence of values t converging to 0 such that I converge this value. And this sequence gives me closed intervals between x and x plus t, or x plus t, x depending on the sign of t. Okay? And they can be as small as I want around the point. And this is the opposite, gives the same, the different sequence, but is still a Vitali covering going to the same point. So these are the natural way to build the Vitali coverings. So exercise, well, or clearly, let's say clearly this is not b minus of x is just equal to b plus of x, and f prime exists b minus of f. Okay. Question: is f the upper? So let's say exercise. This is b minus f, b plus f measurable. They are measurable simply because I'm not using anything. But actually they are the limit. So because a equals 0, since this is decreasing, so the limit I can take, it's a sequence of decreasing sequence of function. I can take just countable here. And this is the supremum for t. And but still here I can just take a dense set of t, no? To compute the supremum, countable dense of t. And then each function here is certainly measurable. Okay, lemma. F increasing, d minus of f greater or equal than 0, and the measure where d plus of f is greater than alpha is less than what can be? F is increasing. 1 over alpha. But the value, I don't have still the derivative. I can say the values. I can say f of b minus f of a. Okay, this is in x, a, b. Or let's say b open, because You see, if I close it, I have to choose the sign. I can take the derivative on one part and on the other part, on the boundaries. So just to avoid this. Proof. Okay. I want to use vitality here. So I need the set. The measure of E is less than plus infinity because of I'm in a bounded interval. Now, what is the Vitali covering here?
The enter x plus
Those intervals.
By definition of E, for each x in E, there exists T, well, let's say an interval I, which depends on, for each x and for each epsilon, there exists an interval Ix, okay, such that x is in Ix epsilon, and the measure, the length of I epsilon x is less than epsilon, and okay, let's say this interval is one side is x, the other will be x plus t. And the opposite in the other case. Be minus plus t, but t is less than 0 here. Because give me epsilon, give me a point in E, it means that I have a sequence of t going to 0 on one side or the other or in both, and the value is larger than alpha. So if I fix, I choose one of the t's, I built this with the intervals, and it also on the extreme the condition. It is exactly the selection of the interval. Then,
Some delay.
Vital. Cover E with countable remaining. Ix I disjoint with sides epsilon I. So here the sides would be epsilon and t is less than epsilon. And now we compute. Okay, so the measure of E. Well, I'm removing a set of measure 0 by the corollary vital. So it's equal to the measure of the unit. They are disjoint by vital. So it's equal to the sum. Gosh, but the sum of this guy, look here, is larger than alpha times t. And t is exactly the length. Okay, so this guy is less or equal than alpha, the sum. Sorry, it's 1 over alpha, the sum of f. Let's say f on the right minus f on the left. Say that the f on the right should be the, how to say, let me write, because I have to switch the sign here. Right minus f on the left. And since it's monotone, the sum of this guy is less than this guy. Is the sum of the increment in a subset, and then this guy is the sum of all the increment also in the rest. So it's less than 1 over alpha f of b minus f of a. Let's read. Corollary, the upper and lower derivative, they exist almost everywhere. When alpha is plus infinity, this is 0. So they are not plus infinity everywhere. So corollary, if f is monotone, the minus f or the plus f equal to plus infinity only in a set of measure 0. Just the observation, no? So now we are in the fundamental theorem about monotone functions. They are differentiable almost everywhere. And this gives me, in some sense, it gives me a reason to go on in the theory, no? It is not still clear which class I'm living in, but certainly I can take derivatives. So if a function is a difference of two monotone functions, it has a derivative almost everywhere. And actually from this observation, I can also prove that it is really L1. So let's do the fundamental stuff. From this guy, you observe that already it tells me that you have something like a Chebyshev inequality in some sense, no? The measure when a sum is larger than alpha, less than 1 over alpha, the integral. You remember, this is very close. F monotone. Let's say increasing. Then prime exists almost everywhere. Okay. So let's consider the points where f is not differential and show that it has measure 0. Because now we are always applying Vital, so we find a set and we find a covering. Okay, I can, but I need some uniformity here. So let's do, I take two index. Alpha less than beta, and are all the set such that the lower derivative is less than alpha, and the upper derivative, the point x, is larger than beta.
Is there any way to get around this Vitali covering thing?
There are other covering theorems, but no. Because the philosophy is that you do the computation using some nice sets. In this case, we are in R, we do the computation taking some nice intervals. And at some point, you need to prove that they don't superimpose.
Sorry?
They do not superimpose each other.
Oh, with the intervals?
Yeah, that you choose.
What do you mean by superimpose?
The intersection is empty. They are disjoint. In order to do the computation about the measure. Because otherwise this is false. And then you cannot say anything. Okay, so let's do previous computation. From the lemma, the measure of the set P is less than 1 over theta. Okay. I don't know if I need to use this thing or if just no, that is yes. Now let's do the same proof using the lower derivative. So let's do the same proof.